Hi, I'm Tom Hirschowitz, and this is a talk about a Cellular Howe Theorem, a LICS 2020 paper with Peio, Borthelle and Ambroise Lafont. The motivation for this work is to generalize theorem statements. Indeed, in programming languages, often theorems are stated for one typical language, chosen generally to be complex enough for the idea to be relevant, but simple enough for exposition to be accessible. The goal here is to provide high-level tools for stating theorems at the right level of generality, so for a whole suitable family of languages and models. Lots of work have been done in this direction. I think it all started with formats in the 90s, but formats were mostly syntactic. Then a more categorical and semantic side to these investigations emerged with Turing-Plotkin's bialgebraic semantics in 1997. It has been deeply developed and is very good at quantitative semantics, but it is less good at higher-order languages, which are only starting to be investigated. Another approach by Arends and his colleagues at Popper this year is reduction monads, which are a notion of programming language in which reductions are automatically stable under substitution. They also propose an expressive specification mechanism for generating such reduction monads. However, they don't yet have any big meta-theoretical theorem like congruence or bisimilarity. Finally, in previous work on cellular monads, I covered the Pi-calculus but no higher-order languages, and also I had no notion of signature virtually, so models were constructed by hand. So the present paper improves this on both counts. So here's a summary of contributions. We first introduce Howe contexts, which are a general setting for reasoning about programming languages. We also introduce a notion of signature for specifying languages there in any Howe context. Then we define substitution clause bisimilarity, which in the example of call by name lambda calculus instantiates to the relevant relation, which is, for the experts, the open extension of Abramski's applicative bisimilarity. Then we study languages in a Howe context, and more precisely we want to prove that substitution clause bisimilarity is a congruence. For this, we introduce two new notions, co-simulations and the inputarity of a transition rule, which allow us to design a semantic format for congruence of bisimilarity. So the main result is that if all inputarities of all transition rules in the signature are co-simulations, and under a few mild technical hypotheses, then substitution clause bisimilarity is a congruence. The proof follows an abstract analog of Howe's method. In this talk, although the paper contains a general framework, I'm going to focus on one example, big step call by name lambda calculus. I'm going to first introduce the Howe context for call by name lambda, then describe models of syntax and transition rules. Then I'll define substitution clause bisimilarity and state the main result. I'll also sketch co-simulations and inputarities in order to give an idea of the semantic format. And finally, I'll conclude. For call by name lambda calculus, we use the following slightly non-standard presentation in which, in order to evaluate a lambda, we just open it, so we return the body of the abstraction. Thus, the evaluation relation relates closed terms on the one hand to terms with at most one free variable on the other. The beta rule is modified accordingly, so in order to evaluate an application E1, E2, we first evaluate the body, the function E1 to some E3, then we replace the unique free variable of E3 by E2, the argument, which is what that means here. We evaluate this, get E4, and that's the result of the whole computation. We could do with a more usual presentation, but it would be a bit more verbose, so we stick to this one. Now, the Howe context for call by name lambda, the main data for this is a category which has two levels. On the lower level, we just have the natural numbers with no morphisms. On a higher level, level 1 say, we have one object, in this case, arrow, together with two morphisms from the lower level, say S and T for source and target. The basic objects of study in a Howe context are the presheaves of the given category, so contravariant functors to sets. In this case, we think of, for any presheaf x, we think of x of n as a set of terms with potential free variables in 1 to n. X of arrow is thought of as a set of evaluation witnesses. So x of s takes an evaluation witness and returns the source or input to the evaluation process. And x of t also takes an evaluation witness but returns the body of the obtained value. So it has one free variable. Now let's describe models of syntax. A model of syntax will be a presheaf x equipped with operations, so families of maps from xn squared to xn for application, say append, and from xn plus 1 to xn, say lambda n for abstraction. Equivalently, this is sigma 0 algebra structure for the endo functor sigma 0 defined by sigma 0 xn equals x of n squared plus xn plus 1. Beyond operations, a model of syntax should also feature substitution, which in our case means a morphism from x tensor x to x, say m like multiplication, where the tensor is defined as follows. X tensor y of n is the sum of all p's of x of p times y of n to the p. And we think of triples p, x in big XP, and sigma from p to y of n as explicit substitutions. So x formally substituted by sigma. So substitution takes such an explicit substitution and maps it to an actual substitution, which I'm going to write with square brackets, like so. And finally, a model of syntax should feature an embedding from variables. In our case, it means a morphism from I to x, where I is defined by I of n equals 1 to n, so the set of potential free variables. So we define transition sigma 0 monoids, which will be our notion of model syntax, to be this presheaves with operation, substitution, and variables, satisfying additional coherence conditions. This is quite closed, but not quite the same as Fiore, Plotkin, and Turi's abstract framework from 1999, in which x would have some renaming built in. In our case, it's only part of the added structure. Indeed, it's a particular case of substitution by variables. The reason we use this variant is that it enables familiarity and cellularity, which we'll get back to later. We can organize transition sigma 0 monoids into a category with a natural notion of morphism, and the forgetful functor to presheaves admits a left adjoint L. Finally, we can define syntax to be L of the empty presheaf. So it's the initial sigma 0 monoid. Now for models of transition rules. Let's consider the first rule. The parameters of this rule here are very simple. It's just E, so a term with one free variable. Accordingly, a model of this rule will be a presheaf equipped with a map from x of 1 to x of arrow. So for all terms with one free variable, you get an evaluation witness. Let's say val. For the second rule, the beads rule, it's a bit more complex. The parameters are a reduction or evaluation witness R1, another evaluation R2, but we need to enforce some constraint between the source and target here. And in order to express this, we need a third parameter E2. So a model will be a presheaf equipped with a map from A, B to X into X arrow, say beta, where A, B to X is defined to be this set of compatible triples R1, E2, R2, such that the source of R2, which I'm going to write like this, is the target of R1 substituted with E2. Additionally, we have compatibility conditions for the source and targets of these obtained evaluations to be as desired. So just like for syntax, the models can be viewed as algebras for a certain endofunctor sigma 1. In fact, vertical algebras for a certain notion of vertical. It's almost algebras. And as before, we can organize them as a category, and the forgetful functor to transition sigma 0 monoids admits a left adjoint. And finally, we can define the syntactic transition system Z to be the initial model, so the image by the left adjoint of the initial transition sigma 0 monoid. Right, so that was for specification, the notion of signature, sigma 0 and sigma 1. Let's now consider substitution closed by similarity. We need to prepare a bit for this, and in fact explain what the UNIDA lemma in this category and arrow hat looks like. So UNIDA of 0 will consist of just one element of a 0, so a closed constant morally. UNIDA of 1 will just have one element of a 1, so a unary constant. And UNIDA of arrow will be just one evaluation witness plus its source and target. And the main point to know is that morphisms from, for example, UNIDA n into x, any presheaf x, will be in bijective correspondence with the elements of x over n, and just the same with arrow. Now let's define bisimulations. We say that a span xry with r of arrow empty is a bisimulation if the following two clauses are satisfied. And I'm going to write straight away that the symmetric clause should be satisfied, otherwise I'm going to forget it. So the first clause is as follows. You put the basic cospan vertically here, UNIDA of 0, UNIDA of arrow, UNIDA 1 with source and target maps. Then you put your span next to it horizontally. And the first clause says that for all red arrows making the square commute, there should exist green arrows making the remaining squares commute. There are 4 squares in total, the red one and 3 others. What does this mean? Well, by the UNIDA lemma that we just saw, the first red arrow is the same as a pair of related closed elements. So x related to little y and big Y of 0. Similarly, the second red arrow is an evaluation witness from the same x because the square commutes, so its x evaluates to some x prime. Well, the green arrows as just the same, so the first is an evaluation of y to some y prime, and the second one shows that x prime is related to y prime. So we recognize here the data in red for simulation, the usual data for simulation, so x related to y and x evaluates to x prime, and in green the completion of these data, so evaluation of y into y prime and proof that x prime is related to y prime. Now for substitution clause relations, a relation is just a span whose pairing is monic, and a relation from x to x, so an endo relation, is called substitution closed when, if we take a related pair and consider an explicit substitution by terms from x, and if we distribute the substitution to both sides of the relation, So we get this morphism here. And then we evaluate the explicit substitutions. Then the result should be in R. So it means categorically that the composite should factor through R. Morally, it just says that if x1 is related to x2, then x1 sigma is related to x2 sigma. Now we can prove that for any transition sigma 0 monoid x, there is a larger substitution clause by simulation relation till the tensor x, called substitution clause by similarity. And that's the right definition in our case, because in call by name lambda calculus, it instantiates to open extension of applicative by similarity the relation originally studied by Howe. So in the paper we have a generalization of all this, as I said in the introduction. So the embedding of natural numbers into n arrow is replaced by an arbitrary two-level category. The tensor is replaced by a skew-monoidal structure, and so on. In this general setting, the main result is that for any suitable signature, substitution clause by similarity on the initial model, so till the tensor z, is a congruence. We express this categorically by saying that if we apply an operation from the signature sigma 0 to related pairs and distribute the operations to both sides and then evaluate, then the results should still be related. So this says that the composite should factor through till the tensor z. How do we prove this? So very briefly, we define a closure of any given relation R over Z by this formula, which you don't need to read. And then we prove that this closure R bullet is a transition sigma 0 monoid. So when then the key lemma states that this closure is a simulation. So it means in n arrow hat, it means the diagram below left. So for all red arrows there exists green arrows, making all four squares commute. But because our bullet is a transition sigma 0 monoid, the span that we have here is in the image of the forgetful functor. And so we can, by adjunction, state this equivalently in the category of transition sigma 0 monoids, as on the right here. So it's like simulation, but with respect to L of the basic cospan, where we recall that L is the left adjoint to the forgetful functor. Okay, and now let me briefly sketch the semantic format, the main hypothesis under which this theorem holds, which is called cospan cellularity. As I said, it relies on two new notions, the inputarity of a transition rule and the notion of co-simulation. So first, the inputarity. I'm going to just proceed by example on the beta rule. It's going to be a cospan whose left object will be the arity of the source of the conclusion. Here it's two closed constants, so I'm going to write out L of unida 0 plus unida 0 here. The right hand object will be the arity of the target of the conclusion. Here it's a term with one free variable, so I'm going to write L of unida 1. Now for the middle object there, E beta, the idea is that it should represent the set of compatible triples A beta of x that we saw earlier. So this should be isomorphic to the Hom set in transition sigma 0 monoids from E beta to x. So the question here is how do we pick the parameters for this rule? So R1, R2 and E2 in any given x. Well, we can first pick R1 and E2 by picking a morphism of this form by unida and by adjunction. We can also pick R2 like so. And now we need to enforce the constraint. So when are two morphisms of this type compatible? Well, we can take the source of R2 there, it's the composite morphism here. Similarly, we can take the target of R1 by precomposing by this morphism. And finally, there's a substitution morphism here, which allows to compute the right substitution. So all triples are given by commuting squares of this shape. But now, if we take the push out in there and call that E beta, compatible triples are also in bijective correspondence with morphisms from E beta to X as desired. So that ends the description of the inputarity of the beta rule. Let's see co-simulations briefly. You see there's a notion of orthogonality in the definition of simulation, co-simulation. We just generalize this and call a cospan AEB orthogonal to a span XRY if for all red arrows making the square commute, there exist green arrows making the 3 remaining squares commute. We can extend orthogonality to sets of cospans and spans as usual, and for example we could have defined simulations as the right orthogonal to the singleton set consisting of the basic cospan. And for co-simulations we proceed just dually. We define them to be the left orthogonal to simulations, so they're all the cospans that behave well with respect to all simulations. We can now define the format, cospan cellularity. We say that the signature is cospan cellular if and only if for all rules the inputarity is a co-simulation. But why is this the case for call by name lambda calculus, and in particular for the beta rule, you'll ask? Well, we have this lemma which says that basic cospan and identity cospans are co-simulations, and furthermore co-simulations are stable under pointwise coproduct, precomposition of their right-hand leg by anything, and cospan composition by push-out. So let's see how the arity, the inputarity of the beta rule is a co-simulation. Well, by the first point, this is a basic cospan, so it's a co-simulation. Similarly, this one's a basic cospan too. Next, this one's an identity cospan. We can then apply stability under pointwise coproduct to get that this cospan is a co-simulation. Then we can use that co-simulations are stable under precomposition of their right-hand leg, here this red morphism, to get that the composite cospan here and here is again a co-simulation. And finally, we use cospan composition by push-out here to get that this big cospan, which is exactly the inputarity for beta, is a co-simulation. So in summary, we have a semantic format for congruence of substitution clause by similarity in any Howe context, which essentially says that inputarities of rules should be co-simulations. I've only shown you here the example of call by name lambda calculus. In a paper we also treat call by value lambda calculus, albeit maybe a bit naively. And for future work, well, an intriguing question is to find an inductive characterization of co-simulations, which we don't have yet. The lemma is probably not complete. We also plan to investigate other kinds of bisimilarity, like normal form, environmental, contextual bisimilarity, and their weak variants also. And finally, it would be interesting to look at other kinds of results, like type soundness and compiler correctness. Thanks for your attention.